People talk a lot about Cassini, people talk a lot about Halley, but in the end, Kyle, who was more than just a minor figure, actually did quite a lot. He still remains a bit under the radar. So Martians are as well known as Venusians and Jovians. They're all equally well known. Einstein then notices a minor calculation error. So in the end, it's a good thing there are other eclipses. We couldn't observe them because we would have found something incorrect.
Hello and welcome to this new show. Today, we're going to talk about astronomy, but we'll be able to focus on the men, the scientists behind it, and their destinies, sometimes incredible, sometimes unusual. To answer all our questions, Yael Neis is our guest today. Hello. So, we also have you here to talk about your book. So, there's a book that's about to be published. We'll talk about it a little later in the interview, but in it, you address these questions and these destinies that are a bit unusual, a bit fabulous. So we're going to talk about astronomy, about the origins of astronomy. The first question that comes to my mind is, why did we start looking at the sky? What actually made us use the sky?
Well, actually, the sky can be extremely useful. And let's say that as soon as we start looking at the sky, we'll find that the sky allows us to define time and space. Time, because you see, when the sun comes back, that's a day. And then if we want the sun to come back in exactly the same way at the same moment, we have to wait a year. And so we have the seasons, we have the months, of course, with the moon, and all of that, of course, helps organize life. So first of all, for nomadic peoples, of course, and for sedentary ones, to plan the harvests and therefore the taxes that go with them. So there you go. We're going to organize life thanks to these calendars that are based on the sky. And then, of course, there's the question of finding our bearings in space, because as we know, when we look at the sky, we see the stars revolving around the pole star. We know that it gives us the direction of north. Naturally, on the opposite side, we have south, and then we have east and west. So obviously, this helps us find our way with the cardinal points. And then the height of the pole star will allow us to determine the latitude of the location. So at this point, we start to be a bit more precise and can travel more easily. And so obviously, we really have some very practical things or useful things that make us interested in the sky. And then after that, there's everything else, because the sky or the stars rise every day. So there's a sense of immortality hidden behind it. There's the fact that they shine, even though, well, we've known for a long time from trying to make fire that it's not so easy to produce light. And then after that, there's also this aspect of being above us. So it might seem a bit strange to us, but at the time in ancient thinking, the fact that the sky is above meant there was a certain dominance over the earth and therefore over us. And so very quickly, people started to deify parts of the sky or objects in the sky all over the world. It's not typical of any one place in particular. And so in the end, there will be a practical side and a more religious, more spiritual side that will be associated interest in the sky. And then, of course, there are always some curious people who wonder in the end what's happening up there and what it all means.
Okay, so among those who used the sky, there were also, for the most part, sailors and navigators. How can you use the sky and the stars to find your way on Earth at a time when there was no GPS yet?
So we used the sky to find our way for a very long time, because without GPS, that's all we had. So if we look at Polynesia, there's actually only one word. There isn't one word for sailor and another for astronomer. There's only one word for both, because the navigator has to be an astronomer to find their way. So look at the sky. The first thing for us is quite simple. We're lucky to have a star not far from the poles, so there you go. We can spot the North Star quite easily because, well, we have the end of the Big Dipper, which helps us point to it, so we're in the northern hemisphere. It's pretty lucky when you're lucky. And so right away, we can see that if we go further north from where we are toward the North Pole, the North Star will rise higher in the sky. If we go more toward the equator, the North Star will go lower. So really, the orientation of the sky tells you where you are in terms of latitude. And so this already gives you an idea for getting around. Of course, there's still the other coordinate, longitude, that was much more complicated to determine. For a long time, we tried to reach the right latitude and searched. And then we still tried to use the sky to find longitude by observing, for example, eclipses, lunar eclipses, or eclipses of Jupiter's moons by Jupiter. And we tried. We knew what time it was supposed to happen, well, in London, in Paris, and then we knew what local time we observed it from the ship. we would say, well, there you go, that means we're at this longitude. So we still tried to use the stars to find longitude. But we have to admit that it was complicated for a long time, and in the end, the problem was solved with precise clocks rather than with the sky.
All right, but it's true that there were many different civilizations that used the sky to predict things, including the Mayans who predicted eclipses. How could they go about predicting these eclipses?
Quite simply because in the sky, there are actually a lot of regular patterns. And so when you observe, for example, eclipse seasons, it's about every 6 months. And so you obviously have the solar eclipse, which only affects a very small area, but the lunar eclipse is easier to see and covers a much larger area on Earth. So predicting lunar eclipses is easier. Over a human lifetime, you'll still see quite a few of them. And so little by little, we realize and eventually understand this 6 month regularity. And that's what we do. For the Mayans, especially, the idea of cycles was extremely important. So finding cycles in the sky was really something that mattered a lot to them. And so they observed for a very long time to finally come up with arithmetic models, not geometric at all, but simply arithmetic, that allowed them to predict eclipses, to predict when Venus would return as the morning star or as the evening star, and so on.
Here, I'm going to jump ahead a bit in time because I was getting to 1572 to talk about the appearance of a star that Tycho Brahe observed. At the time, people thought it was a star that had appeared. Can we go back a bit to this person and talk a little about what actually led him to do what he did?
So Tycho Brahe is someone extremely unique. So he is a Danish nobleman who will lead a noble's life, let's say, quite typical for his time. So a life made up of grand banquets, networking with the king and with people, of course, and also of duels. He will actually lose a part of his nose during a duel. So he will have, blows. Around him, for example, he will have an astronomer's madman because it's not about wires and walls, but he will have an astronomy enthusiast in his Uraniborg castle. So there you go. He will really have quite a classic noble's life for his time, but at the same time, he's someone who really loves astronomy and also alchemy. And so he will try to understand the universe through both of these approaches. And so he will manage to convince the king to give him an island and to fund his instruments. So be careful, this is no small thing as an investment. It's considered that at the time it was about the same investment as the American government for the Apollo mission. So that gives you a bit of an idea of the investment that Denmark made at that time, a few percent of Denmark's GDP back then. And there he will observe the sky for several decades and make extremely precise observations. So in addition to these extremely precise observations of stars and planets, there are actually two major things that he will observe. First, there's the famous nova. So at the time, actually, the idea was that everything below the moon could change. That's what is on Earth. We see that on Earth things change. But everything beyond that must remain unchanging, perfect, and so on. So actually what happens is that if we have a comet, if we have a new star, it must be atmospheric, then right. But then obviously if it's atmospheric and we start looking at the object, we'll be able to triangulate it. That is to say, it's a bit like when you look at your thumb with one eye and then the other, you'll see it moves. So if it's close, it should move quite a bit. And so what does Tycho Brahe do? He sees this new star, this nova as we call it. He says, I'm going to see where it is. And he realizes that no, it's not that close. And he's going to do the same thing again with a comet 5 years later. And again, he'll show that the object is not very close at all. So if they're far away, that means the idea of a universe that doesn't move doesn't work. And worse, the comet itself moves. Obviously, we can see it moving among the stars. And so, given the path it takes, it should break through the famous great spheres where the planets were supposed to be. So it's literally going to break Aristotle's model, those magnificent celestial spheres that held the stars. And so we end up with a universe where things change. We can have new stars. So at that time, he imagined that they were born somewhere between the first stars and the solar system in a sort of intermediate zone. But there you go. So, of course, we revised the models, but he's really going to stir things up by saying, well, this old model where nothing moves, where we have spheres, we can forget about it.
All right, because we're still in 1572 here. So, at that time, people still believed in this model of spheres on which the stars were projected.
Yes, yes, absolutely. If you take Kepler, so Kepler, who will actually use Tycho Brahe's data to once again completely change the way we see the universe. Well, Kepler himself will put things on spheres or Pythagorean solids that are nested with spheres between them. But so he also imagines this kind of thing. So we shouldn't think that this model was abandoned right away. It actually lasted for quite some time. And how the fact that even putting the sun at the center of the system doesn't change the fact that the planets remained on spheres. So this idea would persist for a long time. Tycho Brahe is the one who says, let's get rid of this.
We've just talked about an early explorer. At that time, were explorers starting to travel around the world more in order to carry out more of these expeditions? So,
Actually, at first, astronomers observed from their homes. They were comfortable at home and didn't move around much. Well, at most, like we said with Tycho Brahe, they would settle on an island not far away, but still, it's not really very, very far. So most of the time, astronomers, and this will last for a very long time, they will stay at home. But from time to time, we will still say to ourselves, moving a little wouldn't be so bad. And finally, the first great expeditions, well, unless you count an ancient example, Pytheas of Marseille, who, let's say, made the first great astronomical expedition. But apart from him, actually, we'll have to wait for the Dutch. The Dutch, who at first don't want to go on an astronomical expedition at all. They want to go on an expedition to get spices. So it's a commercial expedition. But in this trade, there was actually a guy in Holland who made globes, terrestrial globes, celestial globes. And the problem is that obviously to sell these celestial globes, well, he had to pay a kind of copyright fee to use the maps, and he didn't really want to. So what could he do? He needed to have his own maps. And especially when you look at the globes from that time, there's a gap. The gap is around the South Pole. The southern celestial pole didn't have any constellations. He didn't care about what the Aka or the Aboriginal people thought. So, well, that's it. There was a gap in the European maps at that spot. And he said, if I send a guy with the expedition for spices who will start making observations and will start mapping the stars in the sky, I'll be able to finish my thing and have for myself a unique globe. And I'll be the one who gets the copyright. So for a commercial expedition, we're going to have a sideline, let's say, not just spices, but also astronomy. And so that's how we're going to have the first southern constellations defined by the Dutch.
so basically, the expeditions simply started for commercial reasons.
Often it's about commercial interests. And even in the case of astronomy, the first ones will be about that. But very quickly, of course, we'll realize that we can just as well go there for purely astronomical reasons. And so, apart from the Dutch, we have to admit that afterwards, very quickly, we went there for the sake of science.
So, speaking of scientific expeditions, in 1669, Jean Picard managed to calculate the circumference of the Earth with immense precision. How could they manage to get such a precise result at that time?
So, what's interesting is to look at how things were done back then. Because the first person who did it in France was called Jean Fernel. And what did he do? Well, he left Paris and took the road to Amiens, which was a fairly straight road. So, okay, heading north. So, what did he do? He looks at the sky and decides to keep going until the position of the stars has changed by 1 degree. So, the latitude has shifted by 1 degree. So, at the same time, he made sure to count the number of carriage wheel rotations. The carriage wheels, okay, he counts the number of turns they made between Paris, where he started, and the point where precisely it shifted by 1 degree. And that's how he got a first estimate of the length of a meridian degree. So when you have 1 degree, you multiply by 360, and you get the circumference of the Earth. That's the circumference. The first idea, I mean, is simply to try to find it. So some people had fun with surveyor's chains, but he went with the carriage wheel turns. So a century later, another technique was found, actually. And the other technique is to use triangles. Why triangles? Because with triangles, if you know one side and you know two angles, well, your triangle is completely defined. And so the idea is to fit triangles together and that way be able to measure much greater distances, obviously, without having to count the number of carriage turns, without having to move a chain that is never exactly the right length. So it's about linking triangles together. The first time this was done was in Holland using church towers, all along, all the way from the north to the south of Holland. And then obviously, while it was the first attempt, it wasn't super great in terms of accuracy either. And the first really precise attempt will be by Jean Picard. What is he going to do? He too will go towards Amiens. He will leave from Paris and go towards Amiens, Saint-Jean-Géat. He will make 13 triangles and measure the angles of these triangles. And you have to measure at least one side somewhere. And unlike the Dutchman Snell, what Picard will do is measure a base, as it's called, that's much larger. Because obviously, the better your initial baseline is measured, the bigger it is, the more precision you'll have for the rest. And so that's what he's going to do. He's not just going to measure 2 angles, but all 3 angles of the triangles. And he's going to use a fairly large baseline. This space is located between Juvisy and Villejuif. He will measure it in both directions to make sure he has the right precision. And he's going to take a standard, which will actually later be placed in the wall of the Châtelet in Paris. This ensures we have the correct standard and know exactly what we're talking about. And so that's how he's going to manage to determine that a degree of meridian arc is about 111 kilometers, which is actually very good. Yes, he achieved good accuracy because he used this new technique, but also took every possible precaution. All right, later we'll learn he made a small mistake measuring his baseline and angles. He was very lucky, as the 2 errors cancelled each other out. But that will lead to problems in later measurements.
But what's crazy is that it still requires some intuition that the Earth is round in order to calculate its circumference. That is to say, at that time it was already established that the Earth was round.
So that's not a problem. So the round Earth, that's something that has actually been accepted for a very long time. So sometimes, for somewhat mystical reasons, the Pythagoreans saw the sphere as something perfect. But when we look at Eratosthenes, for him, it's obvious that the Earth is round and he measures it like that. So what we need to realize is that we never lost this knowledge. Actually, people think that Christopher Columbus proved that the Earth is round and all that, but that's not true. The scholars knew it, so in more educated circles it was known. It was just that the rulers and the people didn't know about it. But in the end, they didn't really need to know either. They didn't travel very far either. And so as soon as there were expeditions, especially, for example, when people went to see the sky in the southern hemisphere, it became obvious. The sky doesn't move as if you were on a flat Earth. So when you move far enough, if you just move a few hundred kilometers, okay, you won't see the difference. But when you start changing hemispheres, it's clear that you really see the sky shifting and not the sky being compressed to one side. So you really see, it's quite obvious when looking at the sky that the Earth is round, and so of course Picard will start with that. But if we take measurements made for Al-Mamun in the 9th century in the Syrian desert, it's the same. For them, it's obvious that the Earth is round too, so it's all a matter of moving far enough. As long as we stay in one country, it's hard to see the roundness of the Earth, but if we start moving farther, it becomes quite obvious.
It's already striking. I would also like to talk about Edmund Halley, who is very well known for his comet. What role did he play in exploration and in astronomy in general?
So Halley is going to be extremely well known for his comet, but Halley is actually someone who will go and explore the southern sky a bit. At first, he does this while still a student and completely unknown. That's it. He's just the son of a rich merchant who has a lot of money. But basically, he's trying to figure out how to make a name for himself. And he realizes that trying to make a star catalogue, not by observing with the naked eye like Tycho Brahe did, but by using telescopes, since at that time they had them. That means we'll have more precision, it'll be better. Others are already doing this for the Northern Hemisphere, like Cassini and Flamsteed. The Northern Hemisphere is already underway, so he won't be able to make a name for himself there. So in the end, the Southern Hemisphere, there's no one working on it. And so he decides to go to St. Helena specifically to make a catalogue of the Southern Hemisphere. And so he loads up all his equipment. He has some amazing equipment. His father gave him plenty of money, so it's perfect. He has top-notch equipment. He chose St. Helena because it was a British territory. Its reputation was relatively good. But the problem is, when he gets there, let's just say the weather is a little worse than expected. And so he'll be somewhat limited in doing everything he wanted. Still, he'll obviously be able to do some cataloging, he'll still get some things done, but let's just say it won't have been as great as he thought. Nevertheless, he'll be able to observe. For example, he'll also observe Mercury passing in front of the Sun, and that's going to give him an idea. An idea that will be applied in the following century, which is to observe objects passing in front of the Sun, especially Venus, to try to find the distance, to take measurements in the solar system. So when we do that, we measure the distance between Venus and Earth. But since all the distances in the solar system are linked to each other, well, obviously, if you have one, you have all the others. You have the complete scale of our solar system.
So, can we just go back to that? If we have the distance to one of the planets, we have the distance to all the others. That's it. Comment? How does that actually work mathematically?
So it's actually Kepler's third law. So what happens is, in a way, it's pretty simple. Everything revolves around the sun. And the sun has a mass that is obviously enormously large compared to that of the planets. So in the end, everything is connected by the sun's gravity. All these planets revolve around the sun. And so actually, if we play around a little with the equations of gravity, we arrive at this famous third law of Kepler, which Kepler, since he found it empirically, but which actually links the period, that is the time it takes to go around the sun, and the distance. And this period, actually, we can see it quite easily because we just have to observe the planets. It's really not that complicated to see when they come back to the same spot in the sky. And so from there, you have the proportions. You just need just one, only one. You know the real distance for one, and then you have the proportion for all the others.
When it comes to explorers, there's one who fascinates me. It's Lacaille. And what did he want to accomplish on his expedition in 1750?
So Lacaille actually wanted to go to the southern hemisphere to have an extremely precise catalogue. You should know that he had made a star catalogue in the north. So by using, actually earlier I was saying that Tycho Brahe observed with the naked eye. Halley is going to use a telescope to observe more precisely. Well, Lacaille is going to add one more little thing, that is, on his telescope he will install what are called filar micrometers or rhomboid reticles. That's it. It's a small thing that you add to your telescope to have a reference point in the telescope's field of view. And so not only are you precise with the position of the telescope, but also inside the field you will be able to measure much more precisely. So we know that technologically we are better. We're about a century after Halley's expedition, so he knows he'll really be able to improve the precision by an order of magnitude. He did it for the northern hemisphere and can complete it by covering the southern hemisphere. So he suggests going to Cape Town because it's a city that's still well connected, a city. Well, I mean, there are people there, so he knows if there's a problem, he can always count on people over there. So he's not out in the middle of nowhere without help or anything. Cape Town is fine, it's peaceful. And besides, it's really far south, so for observing, it's great. Also, the weather is good in Cape Town. So that doesn't hurt, he'll be able to go there. So he actually leaves Paris in October 1750, and then he goes to Lorient. From Lorient, he takes the boat. There, they have a few little problems along the way. They have to divert to Rio. And when they get near the Cape, they can't dock right away because there are wind problems. In the end, he arrives late. But the people at the Cape are waiting for him. They are ready to help him. They give him a very nice place to stay with a guy who is with a settler there who does everything to help him to get him settled at his observatory and so on. And so, at first, he left to determine the coordinates, the latitude and longitude of Cape Town, very precisely to make his catalogue of the main stars of the south, and also to observe the planets, especially Mars and Venus, to try to establish that famous scale of the solar system. And so he will begin this observation. So obviously it's still windy at the Cape, and so he can't observe the way he wants all the time. But he will end up observing about 400 bright stars very precisely. And then he thinks there are still a lot of stars in the southern sky. And even Halley's catalogue isn't that great. I can see more. So he says to himself, in the end, I'm going to do more. And so he starts observing, and then he's just going to look at them in the north-south direction, so the meridian. So that allows him to counterbalance the wind because he's just going to open the roof a tiny bit just along that line, and then the wind can blow however it wants. He doesn't care anyway. And so during the nights when it's very windy, he's actually going to observe almost 10,000 faint stars that are not known at all. And not only is he going to catalog them, but he's also going to give their coordinates very precisely. So he does all that. And so he realizes that, well, he's going to have to create new constellations. So he adds 14 new constellations to the southern hemisphere. So, unlike the Dutch, who had followed a somewhat, let's say, a bit of a folkloric mythological tradition, well, Lacaille decided to give. It's the Age of Enlightenment, so let's go. We'll give some nice names like the pneumatic machine. So, yeah, it's a bit unusual. But so we can clearly see an interest in arts and sciences appearing in the southern sky like that, thanks to Lacaille. And well, Lacaille well, he's going to do some pretty extraordinary things because the way he observes, it's just incredible. And to be able to observe these faint stars, he obviously needs to start taking notes during the night. But if you're taking notes, you need light. And so if you use light, you ruin your night vision. So what does he do? He looks with one eye through the telescope and he closes that eye and he uses the other one to take notes. So, but you can imagine the juggling all night long, switching from one eye to the other like that. And also, well, sometimes, I mean, it's hours and hours during the night. So how does he stay awake? Well, actually, in Lorient, he took in a puppy. And he trained the puppy to keep watch during the night to wake him up when he started to get sleepy. So Lacaille is quite a character. When he finished, he planned to spend a year making his catalogue of bright stars. But in just 1 year, he will make his catalogue of bright stars, his catalogue of dim stars, planetary observations, all of that. He will do everything he had planned and even more. But the problem is that since he arrived late, he actually missed the return sailing season. And so as a result, he still has a bit of time to kill. So while he's at it, he's going to start measuring a degree of meridian around the Cape. He'll do lots of things like that around there. Because, well, you see, Lacaille does a lot of things. What's funny is that he'll come back by making a little detour through Mauritius and Reunion Island. So he comes back in 1754. And then what's interesting and funny is that he'll publish part of his results, but not all of them, because he won't have time to do everything. And so the famous catalogue with its 10,000 southern stars, well, it's the English who will publish it in the 19th century, because no one in France will bother to publish the famous catalogue.
Yes, so yes, it's still, he actually played quite a major role.
You see, Lacaille will do a lot of things, including measuring France, because he will work with Cassini III to properly remeasure France in all directions, north, south, east, west, and so on. So Lacaille is really going to be someone who, well, who did a lot of things and who, in the end, right now we don't talk much about Lacaille. We talk a lot about Cassini, we talk a lot about Halley, but in the end, Lacaille, who was more than just a helper, actually did quite a lot of things. Well, he stays a bit off the radar, which is a bit of a shame because he's really quite a character. It's quite amusing when you see his eloquence and his way of working. It was really something.
Did he continue his research once he got back then?
So, yes, he tried to publish. He published part of his catalogues, but not all of them, because quite simply he passed away not long after he returned. So you see, it's not just a few months, it will be several years, but I mean, it takes time to put all that back in order. And so, unfortunately, with everything he had to do, he simply didn't have the time to take care of it himself.
Okay, and did the research he did have an impact later on? Did other scientists use it?
Of course, we used a bit of everything, whether it was the star catalogs or also this question of the degree of meridian, because actually his degree of meridian was a little bit strange. And that meant that if it was correct, the Earth was more like a pear shape, a bit flattened in the south. So it was a bit strange. And actually, we understood later that it was a problem with the deviation of the pendulum caused by mountains, actually, that weren't too far away. And so we realized that there were problems we hadn't necessarily thought of in the ways of measuring these degrees of meridian. And so, of course, it would also help improve the measurements in the future.
Sure, since there were mountains nearby, that happened.
It deflects the pendulum. And since it's with the pendulum that you get the vertical and measure the orientation of the sky, it actually throws off your reading of the sky, how many degrees you've advanced. Okay, yeah, that's annoying.
So the observation location is important? Ah, that's important. Absolutely. We'll take a closer look at the locations a bit later. Another explorer who really intrigues me is Guillaume le Gentil. So he had an endless journey to observe Venus. Can we come back to that?
So actually, he was part of those famous expeditions organized to observe the transit of Venus. The transit of Venus is really Venus passing in front of the Sun, so the Earth, Venus, and the Sun have to be perfectly aligned. And that happens that there is a pair of transits separated by 8 years about every century. So you can't miss it. You can't miss it. So Halley had the idea to use it. He knew he wouldn't see it because the transits of the 18th century were much too late for his lifetime. So he knew very well that he wouldn't see them. But he encouraged others to observe. The French would especially get involved trying to get everyone mobilized around this idea. And so they organized quite a few expeditions all over the place. They also determined which locations people needed to go to in order to observe it best. That's it. They sent people everywhere. One went to Siberia, another to Rodriguez Island. And then Le Gentil is supposed to go to India, to Pondicherry, which is a French trading post. Perfect. It's really in the right place. Everything needed to observe this famous transit. Except that when he arrives near Réunion Island, he learns that there are a lot of problems in India, and that, in fact, the trading posts. There's still a war with England, which is trying to take over these trading posts. And so, well, they tell him, no, it's not worth it. No, you're not going. He goes there anyway. He was one of the first to leave, heading out early. Still, he gets stuck and has to wait. He has no choice but to wait, so he's considering going elsewhere. But they tell him, no, listen, you stay here and you wait. And so in the end, he stays there. And at one point, word comes that the fighting may actually turn in the French's favor. So go ahead. So there's a boat that leaves. He leaves on it with all his equipment. He goes. And then when they get near India, well, that's when they hear that actually no luck. Pondicherry had been taken by the English. And so, well, they turn back then. So obviously, Le Gentil has a meltdown. He insists the captain let him off the ship. He says he'll manage if it's English territory and just wants to be on land. Clearly, wanting to disembark in enemy territory seems suspicious. So we begin suspecting each other. What exactly are you doing? He must remain on the boat and watch the transit from there. So he'll see it, but since he's in the middle of the ocean without coordinates, it's useless. So he comes back, he's completely disheartened, he feels completely useless, and then he says to himself, well, what can I do if I come back to France? In the end, the others, they observed, they have data, and then me, well, like an idiot, I have nothing. And so he says to himself, well, in the end, between the two, it's only 8 years. Well, wait. And so he waits.
Right there.
He waits right there, and then he starts thinking, yes, but the transit, where should I go to see it? And he ends up telling himself that maybe near Manila it might be interesting. And so at some point he takes a boat and heads toward Manila, but then that's not French territory. The Philippines then were Spanish at that time, so he wasn't exactly in friendly territory. And well, he had informed the academy, but by the time he received the message from the academy, he had already left. And when the message reaches him, because they forward it to him, but yeah, he arrives in 1767 while, how do you say it? The transit is in 1769. The message tells him, no, you will observe it from India, from Pondicherry. And then, well, he doesn't want to, he doesn't want to start over. He doesn't want to hear about India anymore. But then the Spaniards tell him, yeah, but wait, why can't he leave? They tell him to go back, to the French side, and he wants to stay here. What does he want? What exactly is he doing? So he starts having trouble with the local authorities, and so he has to leave quietly. He returns to the French side and eventually reaches India. No problems now. Pondicherry is French. All is well. He observes, learns Indian astronomy, and does many things. And then on the day of the transit, there are clouds. And so the poor guy who waited, hurry up. There you go. Tough luck. There are clouds. So what do you want? There are clouds. And the clouds. Now he's making a prisoner. So he's heading back toward Réunion and all that. Very often he's going to be depressed. Then he'll get back on a boat. There are problems. He comes back. He never manages to get home. And then finally there's a boat that takes him. Spanish. And then he's going to cross the Pyrenees again. When he gets to France, everyone thinks he's dead since no one has heard from him in years. Nobody knows what to do anymore, so they're settling his inheritance and all that, and well, he'll really have to go to court to say, no, I'm not dead, give me back my things. So it's going to be a little complicated, but well, he was gone for more than 10 years. At that time, the CA expeditions lasted 3.5 years. Le Gentil was away for over 10 years. These expeditions spanned years. So it's not just, I'm taking a plane, I'll be back in a week. No, no, no. Here, it's really an expedition in the sense of the ones organized by Cook or Magellan or something like that. These are really big expeditions that will take time and will be complicated. That's it.
And it's true that it's impressive because today we can travel pretty easily. Whereas back then, doing these explorations was sometimes the work of a whole lifetime, actually. Oh, yes.
Yes, definitely. And even just traveling within France, there are some. Chape, when he goes to Siberia just to get from Paris to Strasbourg, all his glass instruments are broken. And it's in Strasbourg that they'll give him new thermometers, opening tubes, and so on. And to get from Paris to Lorient, the CAE will already take 2 weeks. He did make a number of stops at inns along the way, that's true, but still, that's how it is. Of course, today we can't imagine that it would take so much time, even just to take the boat.
So, another rather unusual story, I think, is that of Jules Janssen, who escaped from besieged Paris in a hot air balloon to go observe an eclipse in Algeria. Can we go back to that story?
Well, he's clearly an explorer at heart. He loves astronomy, but he also enjoys traveling. And so, in this case, actually, it was observing the sun that was really something he was going to spend quite a bit of time on. And a few years earlier, he went to Everest and showed that there were structures, what we now call the chromosphere, where there are solar prominences and all that. At the time, they were only visible during eclipses. And Janssen will show that there's a way to see it everywhere on the sun, even when the sun isn't eclipsed. And that's a rather special technique where you filter the sunlight to keep only the light coming from those prominences, those eruptions. So it's a new technique. He's kind of a champion at this kind of thing, along with Lockyer. He really knows the sun well, so he still tries to go to every eclipse to observe the solar corona and that kind of thing. And just his luck, in 1870, of course, it's the war and he's stuck in Paris. So during that time, there will be the issue of negotiating with the Germans to try to get him a pass. But during that time, since the rumor spreads that he wants to go observe the eclipse in Algeria, people give him messages for Gambetta. And now he's stuck because he thinks if I get a German pass, it's for science. And now I still have messages for the French government, the Minister of War. It's a little bit delicate. So he decides to leave by balloon, so he doesn't have to use the scientific pass because he has secret messages to deliver. So that's what he's going to do. He's going to take the balloon, leave Paris, go deliver the messages, and then head to Algeria. Now, in the balloon, he still managed to bring 160 kilos of equipment. Well, it's not a huge amount, but it's still pretty good.
Yeah, especially for a hot air balloon, it was beautiful. Exactly.
And then after that, he'll become the man of the mountains, since he'll want to build an observatory on a mountain, and so he'll choose Mont Blanc. Clearly, it's the highest, so of course, she thinks, that's the best place. And so he's rather young, he has trouble walking, but despite all that, he still climbs Mont Blanc several times in a pretty charming way, in sedan chairs. It's a bit unusual, but he manages to go there to set up a small observatory there, which won't last very long, because he didn't realize that the snow moves at the summit of Mont Blanc, and so his observatory at the beginning of the 20th century would have to be dismantled. But there you go. It allowed him to show that when you observe the stars, when you observe what we call the spectrum, so it's how light is distributed according to color. Well, actually, there are disturbances that are caused by the atmosphere, and by going up to the tops of mountains, you can escape some of those disturbances caused by the atmosphere.
All right, so to stay a bit on the topic of difficulties in observing, I'd like to go on a brief tangent about Schiaparelli and the Martian canals. And it's true that this is something that really fueled the imagination, and actually, even today, we still hear about it. So, what's the situation? First, can we remind ourselves a bit of the context and what's the situation today?
Actually, so here we are in the 19th century, and in the 19th century, we have what's called the plurality of worlds, which is widespread. That means basically all the planets are thought to be inhabited. Sometimes even the sun, so there you go. So Martians are just as well known as Venusians, Jovians. Well, they're all just as well known as each other. We mostly know about Martians today because of the canals controversy. In fact, it so happened that in 1877 there was a great Martian opposition, so it was a time when Mars could be seen particularly well, and so everyone tried to observe it, and what happened, what he wanted to do was make a map of Mars. He would end up with an atlas bearing his name. And so he starts observing, and well, he's going to reuse some of the same terms as for the moon. So the dark areas are called seas, and the light areas are called continents. The problem is that on Mars, there are a lot of areas that are kind of in between the two. And so on his map, and his first maps are still quite natural, let's say, he uses the term canali. Now, he's not the first to use the term canali. Angelo Secchi had used it a little before him. And in Italian, in this context, it was canale in the sense of the English word channel. So it was a natural structure like the English channel, right? But obviously, when it was translated into French, canali is Italian, canale, okay, but at that time we had just finished the Suez Canal, so instead of thinking of a channel, people really thought of something artificial. And similarly, he himself didn't really object. And when we look at Barth's observations after 1877, those observations are not as good, the conditions are not as good. We have these canals that become narrower, straighter compared to his earlier maps. So it's quite peculiar, there's a change. And then, well, these canals become narrower, and then some people will say, well, it's not just natural structures, there are really people over there who are building, so there are Martians, and so we're going to have two people who are going to tackle this head on. On the American side, there's Percival Lowell, who will take on the Flagstaff Observatory, and on the French side, there's Camille Flammarion. Of course, and both of them, Lowell and Flammarion, are people who will do a lot of public outreach, who will write a lot in the press of the time, and who will really, popularize this idea. There are Martians which will really influence and remain in the collective imagination. And that doesn't mean that at the time all astronomers were like that. It's true that the group who believed there were Martians was actually quite a minority. Most of them rather said yes. Well, we have thin lines, more or less natural, more or less fine, but we have vegetation on Mars, and the fact that there was vegetation, that was acceptable. There was really only a very small group on the other side who said, no, wait, there's no vegetation, there are no Martians, let's calm down. There you go, so you were right. Yes, but well, let's just say the majority camp wasn't really the most vocal, let's say. And so this idea of Martians really took hold, which is why we had the War of the Worlds, for example, by Wells. If we have this novel with Martians arriving, it's because at that time there was this whole idea of Martians everywhere because of making canals, and today we know that actually it's a problem. Well, even back then, because there were experiments at the time conducted, it's just our mind, actually, our mind. When it sees things that are a bit hard to make out, we try to associate them with something, and straight lines are pretty easy. So we tend, when we can't see well, to make things more geometric than they really are, and that's really just the brain at work. Well, there's nothing we can do about it, that's just how it is. And there are some who realize this, as I was saying, by doing experiments or by trying different things. Uh, with different instruments, different magnifications, and they realize that, oh, look, if I look here, I feel like I see lines, and then if I look more closely, the line disappears. So there were quite a few people like that who realized this, especially Antoniadi here in Paris. But what they were seeing was they saw structures, but they weren't straight. It was their mind that gradually transformed them. And you can clearly see, even with Schiaparelli himself, that it becomes straighter and straighter over time. By convincing himself of it, that's really the power of the mind. But actually, it does correspond to areas on Mars, like Valles Marineris or others, that were identified at the time. But they're not canals in the sense of like the Suez Canal, right?
That's also what I find interesting dans cette histoire, c'est des fois the ability to project our imagination And as a result, to actually change the interpretation we sometimes make of an observation because of the beliefs we have at the moment we make the observation.
That's true for everything, we interpret based on what we know, based on our context. So the interesting thing about science is that it's kind of self-correcting, and so after a while we can realize that there's a problem. Sometimes it takes centuries or millennia to realize and fix things, but we always correct them eventually. That's the point. Science is a process. We accumulate observations, we gather things, and then we realize if there was something there because we misinterpreted it. In the end, it will lead us to such an obvious mistake that we'll notice it.
So, coming back to the observation part, how did people observe the sky at that time? For example, in 1609, what tools did they have to observe the sky?
Well, before 1608, we only had the naked eye. Let's be clear, we don't have any instruments yet. The first telescope will officially be introduced, let's say, in the fall of 1608. And so afterwards, we'll have telescopes and then, well, more sophisticated optical instruments. But before that, we only have the naked eye. So, of course, we can use the naked eye with small instruments. So, what are we mainly going to use? It's going to be what's called sextants or quadrants. So if you've measured with protractors or things like that when you were little in elementary school, in what units are angles measured? Basically, that's it, except you don't have 180 degrees, but you have either 60 degrees for the sextant or 90 degrees for the quadrant, a quarter of a circle or a sixth of a circle. And obviously, the one you used in elementary school wasn't very big. But here they're going to use slightly larger versions. So in the east, they'll have sextants and quadrants that are 1 meter, 2 meters, 3 meters, that kind of size. We can go even further. We have the Ulugh Observatory in Samarkand, where the sextant had a radius of 40 meters. So we can go up to that size. There you go. So the observation will mainly be done like this. So the bigger it is, the more it will help improve precision. But in the end, it's still always the eye that will be the limit. So, well, Tycho Brahe will make observations that are as precise as can be done with the naked eye, but he will still always be limited by the eye itself. Then you can also use an armillary sphere. An armillary sphere is basically, armillary means rings, so it's groups of rings that will represent the equator, some meridians, and then you can add to these armillary spheres some tubes, sighting tubes that will allow you to aim at different objects, and so directly you have the coordinates. Travelers are more likely to use astrolabes because the astrolabe is a little analog computer. It's wonderful, but these are not instruments for doing astronomical research. It's really more for the traveler to find their way, to know where they are, to know what time it is, to know which direction they need to go, that kind of thing. So here we have instruments that are typically astrolabes. They're between 10 and 30 centimeters in diameter, so they're not very big. So it's not going to allow for research, but it does give astronomers, sailors and travelers a very practical way to find their bearings. So the astrolabe will be the travel instrument.
All right, it's a kind of Swiss Army knife, but less precise, that's it, but it's enough to be able to...
Completely sufficient for the traveler, but not enough to do precise astronomical research.
Now, we're going to get to a slightly more modern era. I'm thinking of the 1919 eclipse, which was a historic event because it also allowed the confirmation of the theory of relativity, especially Einstein's theory. Can we go back to that episode? Why was it so important?
Actually, it's a story that begins in 1911 when Einstein, while working on these things, realized that light can be bent by a mass. So they don't realize that actually there were already guys who thought about it a few centuries earlier as part of Newton's theories. Because at that time, light was thought to be made up of little particles. So it had mass, and naturally, if it passed near a massive object, it would be deflected. It was pretty logical. In Einstein's time, the idea was more that light was a wave, so obviously it had no mass, and so, well, it wasn't necessarily obvious, but Einstein thought, well, in my theory, yeah, there is a deflection. So thinking that light, if, for example, I look at stars, okay, they're in a certain place, but if I put a mass between the two, well, it's going to be deflected. So where can you find a large mass in the solar system? The sun works well. The problem is, obviously, if the sun is there, well, we can't see the stars. So the only way to be able to look at the thing while the sun is there is during an eclipse. So Einstein thought, guys, what you need to do is observe the areas of the sky during an eclipse, and then when the sun is low and compare the positions, there will be a deviation. And so he tries to motivate them. He's a theorist, so he won't make the observation himself. Instead, he motivates astronomers and eventually finds one in Germany willing to do it. So the guy leaves in 1912, but unfortunately it's cloudy. Then he goes again in 1914, in August 1914.
The right time.
Bad luck. He's German. He ends up in Ukraine, and so he's expelled, obviously. So it's not possible to observe the eclipse. Tough luck. And then in 1915, Einstein realizes he made a small calculation error. So in the end, luckily there were other eclipses. We couldn't observe them because we would have found something that wasn't correct. Actually, what was found was the deviations value based on Newton's gravity theories. And then when he redid his calculations in 1915, he realized that, well, no, it should be twice as large in the theories of general relativity. So in 1915, everything is fine. We have the correct value. But the problem is we're in the middle of a war. And so, well, eclipse or no eclipse, too bad. I mean, there's not much we can do, even though in 1916 a few measurements will be taken. It's not, well, I mean, even in 1918 there will also be a few measurements. Well, guys, no, come on. It's war, And then the English realized that the 1919 eclipse is particularly favorable because actually the sun is going to be in Taurus. And in Taurus, there's a cluster called the Hyades, so that means there will be a lot of stars. It works better with more stars, since more stars mean more fusion and better results. The problem is, well, the war still isn't over. So the astronomers are saying, come on, finish it already so we can go. So finally, in November, at last, the armistice, everything's fine, it's on. Yes, let's go, we're going to observe. So where are we going to observe? Because the big problem is that the eclipse mainly takes place, it's visible from the Atlantic. That's annoying. Here in the Atlantic, we won't be able to take measurements. So there are actually two possibilities left: to observe it in Brazil or to observe it near the African coast. Because inside Africa, we're in areas where it's jungle, it's not going to work very well. So that leaves the coast or Brazil. And the English won't choose. They'll set up two expeditions in parallel. So the first one that will go there will be, it's Brazil. It will be, the boats are finally moving. Eddington, who has to go to Principe on the African side, well, he's going to be stuck in Madeira for a few months because there still aren't any boats going back yet. So he'll have to wait without knowing if a boat will eventually arrive, but one does arrive, and on both sides they'll get a lot of help settling in and setting up their instruments. They're setting them up unusually, laying the instruments on the ground instead of pointing them at the sky. You might wonder, if they're lying down, how will they observe? Actually, in front of the instruments, they're going to place a mirror that will bring the light from the sky to the instrument that's lying down. So why do it this way? Because actually the problem is that a telescope, when you want to observe properly, it has to be on a very stable mount. You basically need to build an observatory, so it's not practical for travel. They decided to just leave them lying down, which makes them stable. Nothing can happen. It's a very stable area. We're just putting up a mirror to bring them light from the sky. And so they do this on both sides. So in Brazil, they have two instruments, and in Principe, Eddington has the twin of one of the instruments that's on the other side. So they observe it in a rather particular way, but they do observe it. And then, of course, there are going to be some little problems here and there. First, when there's an eclipse, sure, the sun is eclipsed, but there's the corona, the solar corona around it, and the deflection is strongest right at the edge of the sun, and there it's not possible to observe because there's the corona. It's going to be complicated since the deflection will have to be measured farther from the sun, so it will be weaker. Also, in Principe, the weather wasn't very good, so they're observing through gaps in the clouds. It's not very good. On the other hand, he had really good weather in Brazil, but there the problem was that it was so hot that the telescopes overheated and one of them lost its focus. And so as a result, the images are a bit blurry. So of course they're bringing back the photographic plates to England. They start measuring them separately and they eventually come up with a measurement, which is indeed taking into account that some instruments lost focus. That indeed this measurement is much more compatible with Einstein than with... So let's say, yes, okay, that's it. Everything is proven. The headlines at the time were that this completely improbable theory had been proven, and Einstein is on the front page of all the newspapers. He becomes a star overnight. On the scientific side, we have to admit that the problem was that the error bars were still quite significant. So they were clearly in favor of Einstein. There were discussions later to see if Eddington had tampered with the measurements and things like that, but actually, no. They repeated the plate measurements, confirming the results were accurate as announced. But let's say we would have liked a little better accuracy. And unfortunately, even though the following teams tried to improve the precision, we never managed to achieve it. We will eventually manage to do it using the same technique, but by using radio waves. And so we observe quasars actually when the sun is in front of them and when it isn't. And with the radio data, we will achieve very high precision. But let's say it's significant because actually Einstein made 3 predictions based on these general relativity equations. The first one was, well, it was about Mercury's orbit, but in a way it's a prediction made after the fact because it's something we already knew. And so we always think, yeah, but the guy just made it fit, you know? So there was still a philosophical doubt about that measurement. And so this is the first real confirmation of general relativity, something that hadn't been imagined before, and that in this case is truly verified when we take the measurement. So it was important at that level, but it was only the beginning of the adventures that are still continuing today.
So then, if we come back to the present day, where do we set up the different observation sites? Why do we choose certain sites over others? We talked earlier about the different difficulties we can have with observation, whether it's the weather, but also quite a few other factors. How do we choose observation sites today?
So for a very long time, I used to say the astronomer he observed from his garden. And then the garden, when you're in France, England, or Belgium, it's not great either. It often rains anyway, so little by little, but it came very late. We still had to wait. People only realized the importance of a good location in the second half of the 19th century. And what is a good location? A good location, first of all, means good weather, that is, having clear nights and not too much wind. The first criterion is still having good weather. So then, obviously, nowadays we go much further. We set up in deserts or on top of mountains or in desert mountains. Why? Because at that level, the atmosphere is going to be much calmer, much more stable. And so the images, instead of being a big blur, will already be a little bit smaller. And then if we're relatively high up, we'll get above the whole layer below, especially, for example, a layer of humidity. So the atmosphere's signature will be reduced. Now, that's good for a number of things, but there are some things we just can't do from the ground. For example, even atop a mountain, the atmosphere still blocks X-rays. And so if you want, for example, to observe in X-rays or ultraviolet or in certain infrared ranges, it's best to go into space. And so there, obviously, you take the next step. You put your telescope in space, you avoid the atmosphere. Now, that doesn't mean it's simple, but let's say that's the next thing. Being able to observe a wider range of colors, being able to avoid the interference from the atmosphere. There are still telescopes on Earth because despite complications, many things can be done here. And then when we need them for certain specific things, we put telescopes in space. Both are complementary.
And so these telescopes on Earth, it must be quite complicated to set them up, to install them, because we're talking about the driest areas on Earth, deserts, mountains, and we're also talking about cutting-edge equipment.
The real problem is actually getting everything out there. So very often you have to build roads. So it's not new when at the beginning of the 20th century, George Hale wanted to set up his telescopes in California. Of course, he had looked at Mount Palomar. It was good, and the sky was great at Mount Palomar, but Mount Palomar was practically unreachable. So his first telescope, he couldn't put them there because it was too complicated. They would have to carry all the equipment up on muleback. It was crazy. And only later did they build a road, and then several decades later they said, finally Mount Palomar, let's go for it. And then after that, they tried Hawaii, they tried Chile, so it happened little by little. But clearly, logistically, it's extremely complicated because you have to build roads, And on those roads, there are some pictures where you can see the trucks bringing the telescopes. 8-meter mirrors in Chile, but can you imagine an 8-meter mirror in its case, let's say, out on a road? It takes up a lot of space. So it's complicated. It's clear it's not easy. You have to transport by boat, transport by road. You have to build a lot of things on site, and then, of course, also figure out how to live there. When you're in the middle of a desert and you have astronomers, technicians, and so on who don't live there and so on, the cafeteria, you have to bring something to eat, but sometimes also something to drink. So there you go. It's a whole logistics operation that's complex, but we managed to do it because, well, it's worth it scientifically. We do it in Antarctica too. And there are also some observations we make there. It's not easy, but we still do them. We can't just decide to say, I'm going to set up my little 50-centimeter telescope. No, you're not going to build a road for a 50-centimeter telescope, but for big telescopes, for large projects where it's justified, it's part of the investment that needs to be made.
There's also a question I wanted to ask you. Are there one or more astronomers who illustrate the role women have in research, at least in astronomy?
There are plenty. It's hard to choose just one. The earliest one we know of actually is a Mesopotamian princess from over 4,000 years ago. So women have been doing astronomy for a long time. Over time, for example, we had William Herschel's sister, Caroline, who did a lot of things with her brother. That was in the 18th century. Of course, there's what was called the Harvard Harem. There was a whole group in there. They were all extraordinary. Personally, I really like Annie Cannon, for example, who will measure an enormous number of stars. She measured more than 300,000 stars. It's incredible over her whole life. She finally gets her permanent position, her permanent contract. She gets it at 75 years old, and at the same time, she still makes cookies for the staff. They're incredible people. There are many of them. Right now, you should know there are quite a few women in astronomy. We have in astronomy master's programs, it's about half and half. We're not just talking about a few women. There are actually quite a lot. The problem comes later in the career, like with all very demanding careers. That's when broader society doesn't always welcome these kinds of things easily. Worldwide, about 22% of astronomers at more senior levels are women. Mais voilà, we hope, since there are a lot more women at the junior level, that over time things will simply shift.
So that allows me to transition to the book you wrote, which will have been released by the time we publish the video. We'll put the link in the comments for anyone who wants to check it out. In this book, you go back over some stories, including some we just talked about, but even more so the history of astronomy. Can you tell us a little bit about this book?
The idea behind the book is basically this. An astronomer tends to stay at home, and we don't see it as a particularly dangerous job. It's not like being a firefighter or in the army. Astronomy was relatively calm. Actually, no, there have still been quite a few cases where the astronomer had to move, and it wasn't always necessarily easy. The idea was to take important discoveries and look at why we had to move and how it went. Sometimes things don't go very well, but in the end, despite everything, despite all that happened, despite the difficulties encountered, despite adversity, it even went as far as losing a good part of the expedition along the way. But in the end, we still got that data. We were still able to move forward. We were still able to do what we wanted scientifically. You can really see that selflessness very clearly. In the end, even if I'm not there, it's not a big deal. What matters is that the data I collected gets to where it needs to go. And so it leads to stories that can be funny, that can be dramatic, that can be a bit of everything, really covering all kinds of topics, because we moved for so many different reasons. To measure the Earth, to measure the solar system, to see parts of the sky we didn't know about, to get better observations, to see where large meteorites had fallen, to prove that general relativity was true. So We really went on expeditions for many different reasons. It was justified, but it wasn't easy. And so I think it gives a slightly different image of the astronomer in their ivory tower doing little calculations on a little blackboard or a little sheet of paper. You see, they were also real adventurers.
They were full-fledged explorers.
Absolutely.
Thank you very much. So we'll put the book in the description for everyone who wants to read it, and there will be many, I'm sure of that. Thank you very much, Yael, for this very interesting interview.
Thank you.